Welcome to the Problemas channel, season 2, episode 45, the episode which I titled Bineapples and Bananas, because in this episode we will solve a problem that deals with a magic tree that can grow pineapples and bananas on it at the same time. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for subscribing to our channel. Thank you for your vote of confidence and welcome to our channel. And second of all, perhaps the most efficient way for you to get the bearings on this channel and derive the most academic benefit for yourself from working with the material presented on this channel is to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problemas Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E45, shown over here, we're given a magic tree that can grow both bananas and pineapples on it at the same time. Hence, just to make things more fun and more interesting, it could very well be a bineapple tree or a panana tree. Pick your favorite, and this is where the title of this episode came from. And we're also told that a person, someone, is harvesting these magic fruits according to the following rules and only the following rules. If 2 bananas are picked from the magic tree, then almost instantly, let's say, the magic tree grows back 1 pineapple. And if 2 pineapples are picked from the magic bineapple or a banana tree, 1 pineapple grows right back almost instantly, also in that case. In yet the third case, if someone picks 1 banana, precisely 1 banana, and 1 pineapple, then almost instantly and right away, the magic tree grows 1 banana and precisely 1 banana right back. So in summary, pick 2 bananas, almost instantly the magic tree will regenerate 1 and precisely 1 pineapple. Pick 2 pineapples off of the magic tree and almost right away, almost instantly, the magic tree will regenerate precisely 1 pineapple. If 1 fruit of each type is picked, 1 banana, 1 pineapple, precisely 1 banana, precisely 1 pineapple, then the magic tree almost instantly and almost precisely at the same time grows back precisely 1 banana. And the challenge here is the following. During the process of this magic harvesting, it so happened that when the process terminated, precisely 1 fruit of unknown type was left over on the tree, and the challenge is to determine the type of that fruit. Was it a banana or was it a pineapple? If the number of bananas and the number of pineapples is known, and the viewers of this channel who tag along and follow the program obviously understand already right away that no one in the mathematical community cares about the actual answer. Is it a banana or is it a pineapple? Doesn't really matter. But everyone in the mathematical community does care about your ability to shine the light on what is mathematics, and thus everyone cares about your ability to generate a story that is perhaps beautiful and elegant and immersive about why the answer to this problem is what it is. In other words, if you are not doing a story, you are not doing mathematics. And if you are doing a story, you are doing mathematics. Initially, your story may be awkward, it may be ugly, it may be cumbersome. That's fine as long as it is your story. And over time, with experience, your stories will begin being less awkward, less cumbersome, less ugly. They will become more and more elegant, more beautiful, and so on. But as long as you generate that story and share your ideas with us, you are doing mathematics. Now, surely by the placement of this problem in our sequence, it is evident for those, again, who tag along, that this problem can be solved using the invariant problem-solving approach. And I described the mechanics of how the invariant problem-solving approach works in, let me write it down here, Season 2, Episode 44. Episode 44, the previous episode with respect to that one. So if you missed that episode, then it is perhaps a good idea for you to go and find and watch that episode to understand how the invariant problem solving approach works and how it is described. And if you are new to problem solving in general, and if you are new to the invariant problem solving approach in particular, then this problem already will be both challenging and difficult and educational for you. And in the lightning round, if we want to apply the invariant problem solving approach to the process of generating a solution to this or that technical problem, we should try to carry out the following two steps. First, we want to try to partition the local material into two distinct piles. In one pile, we put all the things that do vary or do change. And in another pile, which is usually quite small and modestly sized, we put everything or all the quantities or magnitudes that do not change. We refer to each such magnitude that does not change with respect to or in a given context as an invariant. And as the second step, after we manage to analyze the goings-on in this problem and separate the local material into these two distinct piles, as the second step, we should roll through all the invariants that we managed to identify and see if we can leverage one or several in some combination in order to generate a solution of the problem at hand. Again, as we gain experience with the invariant problem solving approach, we will realize that not all invariants are created equal. What that means we will see in a few minutes, and over the course of the next several episodes. I plan to have 5 episodes dedicated to the study, to the initial dedicated study of the invariant problem solving approach. And as we roll through these episodes, we will see how exactly do these invariants work. As such, without any further ado, let us see what in this specific problem does vary. Before we deep dive into the analysis of what material in this problem does change, please allow me to share one of my personal problem-solving experience tidbits. What we're doing right now is we are studying in a dedicated manner the problem-solving approaches that I found useful and which I found to work in my problem-solving career. And all these problem-solving approaches are what? All these problem-solving approaches are heuristic templates. They sit on the opposite end of the problem-solving spectrum with respect to the guarantee. On the opposite side, there is set what? Algorithm that takes certain amount of material in, and they guarantee the production of the answer. In contrast, the problem-solving approaches are heuristic templates, and when we step into any technical problem, be that a problem in mathematics, theoretical physics, or computer science, there is simply no way of knowing does this problem even have a solution, and if it does, how many distinct such solutions can be generated. So the only thing we can do here is try, and one of the reasons why mathematics is such a wonderful endeavor is that there is always, when we take on a mathematical problem, there is a delightful opportunity to fail. And many a time, and most of the time, and let's say on average, we fail, and sometimes only we succeed. And just because the success is so rare, it makes the victory is that much sweeter. As such, when we try certain approach in order to generate the solution of a problem and we fail, that failure is not necessarily bad, because the analysis that we carry out in order to see if we control this problem through the problem-solving approach and solve it can actually deepen our understanding of the local material, and all of a sudden, bam, we step the other way and we generate a solution. As such, for example, when we decide to apply the invariant problem-solving approach to the process of generating a solution to this or that technical problem, it is always a good idea to see what material, what local material does change and what local material does not change. And even if we fail to find a way to apply the invariant problem-solving approach to the process of generating a solution to this problem, still it may deepen our understanding of what exactly is going on with this problem. Now here in this bineapples and pananas problem, let us see what does vary. First of all, we do have a very well shaped process, and even though in the problem statement we're not told so, it is perfectly fine to assume that the person who is executing this, who is doing this magic harvest, is doing it on schedule. For example, every second or every minute or every hour, pick your favorite unit of time, that person makes a decision and he or she carries out one of these harvesting steps, let's say. And for the sake of easier reference, let us name these steps. For example, this step over here, the first step, let us refer to it as A, for example. To this step over here, when someone picks 2 pineapples, we will refer to that choice as B, and to that choice over here, we will refer as C. So let us analyze what is going on with each such legal harvesting choice. If someone carries out the harvesting choice A, then what do we have here? We'll take the number of all the fruits on the magic tree and we do -2 banana, -2B, because no bananas grow back in this case, so we have a pure -2, so the number of bananas on the magic tree after the legal harvesting step A did diminish and thus changed. Very well. Let's say the person who is doing the executing the magic harvest decided to carry out the harvesting step B. In this case, what do we have? Whatever the number of pineapples on the magic tree on at the moment before this harvesting step is carried out, let's say something n, we subtract what? 2 pineapples, and then 1 pineapple grows back. -2 plus 1 comes out to -1. Still, the number of pineapples on the magic tree after the B legal harvesting step diminished by 1 and thus changed. Now, let's say someone decided to carry out the harvesting step number C. Pick 1 banana, pick 1 pineapple. Almost instantly, the magic tree regenerates 1 banana. So what do we have for the numbers of our fruits? -1 banana plus 1 banana. The number of bananas remained invariant, but only in this case, right? Because we showed here the number of bananas does change. But what happens to the number of pineapples? -1 pineapple plus 0. The number of pineapples in that case diminished and thus changed. Wonderful, but now we go back to the crux of the matter and we try to attack this problem. How can we determine the type of the fruit left when this harvesting process terminated? Well, we are not actually told about the specific way in which the person who is carrying out this harvest making his or her choices. For example, how can we encode the process? Let's say there was some number of bananas, 5 million something something, and some number of pineapples, 7 million something something. A person started going at it, executing steps A or B or C in some order, and then at some point in a finite number of legal harvesting steps, bam, 1 fruit was left. The harvesting process terminates. What type of fruit is it? Well, one way to encode that harvesting process is to start writing down, let's say left to right, the letters that represent each legal choice. So here is one way a person can carry out the harvest. Let's write it out over here. For example, I don't know, C, 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 B, A, and so on. This is one way. You see, we're not told exactly how these steps, the legal steps, are strung together. In yet another way, for example, the person who is carrying out the harvest can go B, C, A, C, C, B, B, A, and so on. Now you understand what is going on and where this is going. What is the name of these structures? This structure, and so on, similar structures. The name of the structures is a finite linear permutation. Now, usually when the problem goes this way, we can say a few algorithmically motivated things about the structure of these finite linear permutations. But in this case, let us go back to the problem statement and think about it. Can we say anything with an algorithmic precision about the structure of these finite linear permutations? We're not told how the person who is doing these, carrying out these steps is actually doing it. We do not know. So as far as I can tell, I do not really see a way how to put any algorithmicity, let's say, on the structure of these finite linear permutations. If someone in our audience does see their way, then please share your ideas with us in the comment section. So here, on the one hand, this little analysis can be quite disheartening, because how on earth can we figure out the type of one fruit left when we do not even know precisely in which sequence, CCBA, ABC, CAB, or whatever, these fruits are picked off of the magic tree. But here again, what seems to be a failure, doesn't really have to be, because you see, most of the time, actually all the time, any Olympic or competitive flavored problems, their statements are dialed in so tight on the one hand, and on the other hand, each and every word is actually a hint. So the fact that the author, let's think about this together, the fact that the author of this problem did not tell us anything about the specific way in which the harvesting steps are executed or picked, CBA, ABC, and so on, that exactly in and by itself is what? Is a hint to us. That means that the person who put this problem together knows all too well that the problem can be solved with absolute certainty without any specific knowledge about the concrete way in which the harvesting steps are strung together into a, officially and pedantically, a finite linear permutation. And what does that mean? That means that it is a good time right now to start looking at things that do not change. And again, as you develop your experience with competitive or Olympic style problems, you will already quickly learn, realize, and figure out that, for example, residues modulo this or that, residues modulo 2, residues modulo 3, 4, 5, that whole numbers generate upon the integer division by these numbers are good candidates. Sums of numbers, differences of numbers, or maybe residues of sums, residues of difference, and so on. And eventually these structures that will be a successful invariant can be actually quite involved, and we will look at one such problem later on. But here we want to examine what will happen to the residue officially, to the residue of the number of bananas and pineapples left on the magic tree after each legal harvesting step, modulo 2. Why 2? Well, again, you guys can say, Roman, you already know something what is going on, and to some extent, yes, but in real time, the bulk of your effort will be spent precisely on looking and searching and failing and trying again, to find some quantity that doesn't change. Here, when we look at this, okay, guys, look, 2 bananas, then there is nothing. 2 pineapples, 1 pineapple. Here is 1 and 1, and here is another 1. So it is always pretty much a good idea to start with investigating the residues modulo small numbers, 2, 3, 4, and so on. And that is what we'll do in the next segment. Let me erase our favorite finite linear permutations on the right hand side of your screen before we analyze this. What's going on with the parity of bananas left on the magic tree after each harvesting step. And what we can do over here is the following. Let's write down here bananas. As you gain experience with searching for and finding certain invariants in various problems, you will come to realize fairly quickly that not all invariants are created equal, in the sense that sometimes you feel good because you did manage to find a quantity that does not change with respect to, but then the very next question is, fine, but how does that invariant help me solve this specific problem? For example, at some point in the future, we will solve this absolutely beautiful problem where a certain group of people walks over, let's say, unit square lattice. And every time this group of people finds itself in one of the nodes of that lattice, they split precisely in two. One half of that group walks strictly north, and the other half of that group walks strictly east. And at some point, these people stop walking. And in this particular situation, what is a good low-hanging fruit candidate for an invariant? The total number of people in the group, evidently. At no point in this walking over the unit square lattice, new people pop into the group, and at no point the existing people disappear. The number of people remains one and the same at all times. Wonderful, but how does that help us solve this specific problem? You see, that is the question that we want to ask. And in some cases, the found invariant may be helpful, and in other cases, it may actually not be helpful. So when we dig for an invariant or for a quantity that in the local problem does not vary with respect to or in a certain context, the very next question we should ask is, how does that invariant help us solve this problem? So in this case, let us analyze what is going on with the parity, or officially residue classes modulo 2, of the number of bananas left on the magic tree after each and every legal harvesting step. In the first case, when 2 bananas are picked, no new bananas grow on the magic tree. So how do we symbolize this process? How do we symbolize the case A, the harvesting choice A? Well, again, when it comes to residue classes, modulo 2, we have only 2 distinct residue classes. In general, these are countably infinite sets of whole numbers, of which 0 and 1 are just what? Convenient representatives. That's right. So let's assume first the number of bananas on the magic apple tree before the harvesting step A is executed is even. It means that in that case, that number is representable as 2m for a suitable integer m. And how do we encode the harvesting choice A? Well, 2m minus 2, this is the number of bananas on the magic tree before the harvesting step was carried out, and this is the number of bananas on the magic tree that is left on it after the harvesting step A was executed. What does it tell us? Well, we can rewrite this number as follows: 2m minus 1 still. So what does that tell us? It tells us that before the harvesting step A was carried out, the number of bananas on the magic tree was even, and after that harvesting step was carried out, the parity of the number of bananas on the magic tree is even again, because it is representable as 2 times an integer. Again, yes, pedantically, we know that the set of, let's say, non-negative whole numbers is closed under addition. The sum of any 2 non-negative whole numbers is again non-negative whole number, but that set is not closed under subtraction. For example, 5 minus 3. 5 minus 3 is 2, and that is still greater than or equal to 0, but 3 minus 5 becomes -2, and it is no longer the case, that number, yes. But in our case, let us agree for the duration of this problem, for the duration of this episode, that we will never step into negative numbers, because in this case, it just doesn't make any sense. We do not have any magic fruits on our magic tree, so the process terminates. So when the number of bananas on the magic tree prior to the harvesting step A is even, it will remain even after that harvesting step is carried out. Wonderful. What if the harvesting step B was carried out by the person who is collecting the magic fruit? Well, in this case, the number of bananas does not change. There was some number of bananas before that step was executed. The same number will remain on that tree after that step is carried out. The parity of the number of bananas on the magic tree did not change. Let us analyze the case when the harvesting step C was carried out. In this case, how can we symbolize what's going on here with the number of bananas on the magic tree? Well, let's say over here, before we jump over here, let's do the case when the number of bananas, let's go back to the choice A, when the number of bananas was odd, then it is representable as 2m plus 1 for a suitable integer m. When 2 bananas are picked of the magic tree, then what is the result? The result is 2m minus 1. And then again, we all agree that this number will always be non-negative, because here we stop at one fruit, which means what? Which means that if prior to the harvesting step A, the number of bananas on the magic tree was even, shown like this over here, 2m plus 1. This is the number of the bananas on the magic tree after the harvesting step was executed. That number can be represented as 2m minus 1. This is precisely an odd number of bananas, which tells us again, no matter how many bananas were on the magic tree prior to the execution of the harvesting step A, even or odd, the parity of the number of the bananas left on the magic tree after the harvesting choice A was made will be one and the same. Even to even, odd, let me write it down perhaps this way. Odd, this is even to even, and then odd and odd. Very well, we already talked about the case B. Now let's talk about the case C. If the number of bananas on the case B we already covered, the number did not change. And in the case C, what do we have? If the number of bananas on the magic tree prior to the execution of the harvesting step C was even or representable as 2m for a suitable integer m, what does the step number C or the harvesting choice C tell us? -1 plus 1. So we represented -1. Now we see that the initially even number becomes odd, but then the magic tree pops a new banana right back in. So we capture it symbolically +1. So here the number of bananas remains 2m again, or even. And if the number of bananas on the magic tree prior to the execution of the harvesting step C was what? Was odd, or representable as 2m plus 1 for a suitable integer m, then what does it tell us? Again, -1 banana, almost instantly another banana right back. -1 plus 1. What do we have? We have another 2m plus 1. So that means that if the number of bananas on the magic tree prior to the execution of the harvesting step C was odd, it remained odd after that step was executed. Even is taken into even, odd is taken into odd. Thus, we have just generated a convincing proof that no matter which harvesting step is chosen by the person who is picking the magic trees off the tree, the parity of the number of bananas that are left on the magic tree remains what? Remains invariant with respect to the specific or any choice, any harvesting choice made by the person. Now that we showed that the parity of the number of bananas in this case is invariant with respect to the harvesting steps, let us see what is going on with the parity of the number of pineapples with respect to the harvesting choices. If prior to execution of the harvesting choice A, the number of pineapples on the magic tree was, let's say, even or as 2 times k for a suitable integer k, then we know that in this case 2 bananas were picked, nothing goes for the minus, no pineapples were removed from the magic tree, but the magic tree gives us a gift of 1 free pineapple, which means that nothing for the minus, only 1 for plus 1, and that number is taken into this even number is taken into the number that has the following structure: 2k plus 1, which evidently is a number that is odd. So in this case, when we went from the even number of pineapples on the tree prior to execution of the harvesting choice A to the number of the pineapples on the magic tree after the harvesting choice A was executed, we went to an odd number of pineapples. So here we can say, let's say the letter E captures even and the letter O captures the odd. So here we have it from even to odd for the number of pineapples. And if the number of pineapples prior to execution of the harvesting choice A was odd or representable as 2k plus 1, again, in this case, we have nothing for the minus. No pineapples were removed from the magic tree, but we have the free gift over here. So we write it down as plus 1. And that number then becomes what? 2 times k plus 1. And in that case, the parity of the number of pineapples on the magic tree before and after the execution of the harvesting choice A switched from odd to even, which means the parity, in this case, the parity of the number of pineapples on the magic tree with respect to the execution of the harvesting choice A does not remain unchanged and is not invariant. Now let us analyze what happens when we execute the choice B. What happens in this case? Let's write down B over here. Let's say again the number of pineapples on the magic tree before the harvesting choice B is executed was even or representable as 2 times k for a suitable integer k. We subtract 2 pineapples because here we remove 2 pineapples minus 2. But then the magic tree gives us the gift of 1 free pineapple. We symbolize this with plus 1. Minus 2 plus 1. This number is taken into the following shape: 2k minus 1. Again, here the number of pineapples on the magic tree prior to the execution of the harvesting choice B is what? Even. And after that choice is executed, the number of pineapples on the tree is odd again. We see the parity flipped. Likewise, if prior to the execution of the harvesting choice B, the number of pineapples on the magic tree was odd or representable as 2k plus 1, we'll keep it in parentheses for a suitable integer k. Then we remove 2 pineapples from the tree and we symbolize it with minus 2. We get the free gift from the magic tree of 1 free pineapple plus 1, and that number becomes what? Plus 1 plus 1 minus 2. That number becomes precisely 2 times k, which is a number that is even. So in this case, we went from an odd number of pineapples on the magic tree prior to the execution of the harvesting choice B to an even number of pineapples on the magic tree after the harvesting choice B was executed. Wonderful. Now you guys see what is going on. The only harvesting choice left over here is C. I will do it on top over here. Make sure that you have captured this straightforward manipulation. It's not that difficult. You just have to do it. And when the choice C is executed, we know that we only remove one pineapple from the tree and no pineapples come back up, because in this case the magic tree says, you get one free banana back. So in case C, let's symbolize it over here. If the number of pineapples on the magic tree prior to execution of the harvesting choice C is even, or representable as 2 times k for a suitable integer k, we remove one pineapple. How do we symbolize the removal? -1. And that number is taken into, let's put it this way, into 2k minus 1, which is odd. And this number is even. Again, the parity of the number of pineapples on the magic tree before and after the execution of the harvesting choice C, what? Changes or does not remain one and the same. If the number of pineapples on the magic tree prior to execution of the harvesting choice C is odd, or representable as 2 times k, let's say +1, then after the harvesting choice was carried out, we remove one pineapple. How do we capture this removal symbolically? -1, and that is it. No new pineapples are added. 2k plus 1 minus 1 plus 1 minus 1 cancel each other out. We get a number that has the shape 2 times k. And what is this number? Even. And this number is odd. Again, we see that no matter what happens, the parity of the number of pineapples on the magic tree before and after the execution of the harvesting choice C changes to the opposite. If it was even, it becomes odd, and if it was odd, it becomes even. Thus, this exhausts all the possibilities: harvesting choice A, harvesting choice B, harvesting choice C. Thus, we generated a convincing proof that no matter which harvesting choice is made by the person who is collecting our magic fruits from the magic tree, the parity of the number of pineapples on the tree with respect to actually any harvesting choice does not remain invariant and does change to the opposite. And now that we're done with this analysis, we just have to walk the last mile. Before we draw our final conclusion and generate the answer to the mathematical problem S2E45, I would like to emphasize one more thing. It is important to understand right away that not all invariants are created equal, and an invariant becomes useful if and only if it is capable to detect or to discriminate between all the items of interest. And here, what it means specifically. Let's say we step away a little bit from the specific problem, but we still use it as a backdrop for our demonstration and for explanation. Let's assume, hypothetically speaking, that the problem statement here in the mathematical problem S2E47 was dialed in such a way that we analyzed the behavior of the parities of both fruits, and we discovered, gee, look at this, both the parity of bananas and the parity of pineapples remains one and the same, regardless of the harvesting choices that were made by the person who was picking this magic fruits off the tree. What would that mean? Well, in that case, the parity of bananas will remain, let's say, odd, 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 and odd, and it will remain odd at each and every step that was made by the person who was picking bananas in some mix. And that means that we're told that one fruit was given, so it's plausible that the last fruit that was remaining was a banana. But likewise, it is also possible that if the number of pineapples initially was odd and it remained odd after each and every harvesting step, just like with bananas, Then eventually, when the harvesting process terminates, the number of pineapples would have been odd also. And how can we distinguish between these two types of fruits? How can we distinguish between bananas and pineapples with absolute certainty in this case? You see, we cannot. We now have to, if anything else, introduce the notion of probability into the mix. And this is precisely what we do not want to do. And that is why a few seconds ago you saw my man Egan Spangler, PhD, a character that was portrayed by the great American actor, comedian, and filmmaker Harold Ramis, a character that we all know and love from the movie that we all know and love, Ghostbusters. And Egan actually said many funny things, and one of such funny things was, whatever you do, do not cross the streams. To which Dr. Venkman will famously come back with, why not? And to which Egan will reply, because that would be bad. Well, in our case, this is precisely what we want. If we manage to identify a magnitude that tracks, for example, two fruit types in parallel, and this invariant or this quantity never crosses the stream, so to speak, then there is no way for us to distinguish the behavior of one item from the behavior of the other. And then in that sense, that particular quantity, that even though it doesn't change, will not be helpful alone. That quantity will not be enough for us to generate a absolute certainty solution or answer to that problem. However, in this case, we managed to find a magnitude or a quantity that does, in the language of Egan Spangler, cross the streams, which means that in one case, when that quantity is applied to bananas, that quantity remains constant or invariant. But when the same quantity is applied to pineapples, then it does not remain invariant, it changes, and thus that particular quantity or magnitude is capable of distinguishing between or discriminating across all the items of interest. And now that we understand what is going on with this invariant, we can generate our solution. As such, we already proved that if the number of pineapples on the magic tree initially was, for example, even, then that number will change to an odd under any choice of the legal harvesting move. And that means that since 1 is a number that is certainly odd, that number can become odd in what? In an odd number of flips. And if initially the number of pineapples on the magic tree is odd, then we already also proved that the parity of that number after any legal harvesting move will flip to the opposite. It will become even. So it can so happen maybe that we can bring it down to an odd number, which here 1 is certainly an odd number in what? In an even number of flips. But most certainly we cannot attach the notion of absolute certainty to such an answer, and thus we eliminate this from consideration. I will put it under brackets for pineapples. This is for pineapples. Now let's see what happens with bananas. With bananas, we prove that no matter which legal harvesting choice is made, the parity of the number of bananas that remains on the magic tree remains one and the same or invariant. And that means that if initially, let's say we had B bananas, and then the parity, uppercase P, 0 of bananas, of the number of bananas that was on the magic tree before the harvesting process started, will be exactly the same after each and every harvesting choice, and it will be one and the same when the harvesting process terminates. So we'll symbolize it with uppercase P, F for final, but the number of bananas over here, we will mark it as B prime, just in case for the general situation. And what does that mean? That means that if the number of bananas on the magic tree prior to the harvesting process was even, it will be even after each and every harvesting move, and it will be even when the harvesting process terminates, full stop over here. But we're told that the number of fruits that was left when the harvesting process terminated is 1. 1 is certainly a number that is odd. And it may sound, again, a little bit funny for the people who did not study mathematics deep enough, but the words that we really should say over here is that if a number is odd, then it is not even, and if it's not even, then that number is not odd. And this is basically a side effect of a more general theorem, which states, depending on which course you take and where this theorem is given, let's say in the elementary theory of numbers, that the residue classes of distinct residue classes modulo n for fixed n do not intersect, or this is a jargonish way, more officially, the intersection of any two distinct residue classes modulo n for fixed n is the empty set, which precisely means that if the number is odd, it's not even, and if it's even, then it's not odd. Next, we carefully observe that we have only 2 types of fruit left, which means that if a fruit is not a banana, then it's a pineapple. It must be, no choice. And conversely, if a fruit is not a pineapple, then it must be a banana. Here, odd is not equal to even, so the remaining fruit type cannot be of type banana, but we have only 2. So again, like I said before, if it's not a banana, it's a pineapple. So in this case, the answer is the pineapple is left. In this case, we have, how should I write it down? Here, pineapple left over. In this case, the answer is pineapple is over. In other words, if initially the number of bananas on the magic tree was even, then the sole fruit that was left when the harvesting process terminated was a pineapple. But if the number of bananas on the magic tree prior to the initiation of the harvesting process was odd, symbolized with the letter O, it remained odd after each and every harvesting operation. And that means that it will be odd when full stop happens and the process terminates. And in this case, everything coincides nicely. 1 is odd. This number is odd initially, and that means here the answer is the remaining fruit must be a banana. Must be a banana. Pineapple left over. One more time, if initially the number of bananas on the magic tree was even, then the sole leftover fruit is a pineapple. And if the number of bananas on the magic tree prior to the initiation of the harvesting process was odd, then the sole remaining fruit was a banana. Now, for those of our viewers who are new to problem solving, and in general, and to the idea of an invariant in particular, it actually pays to step back and look at this problem. Realize that we did not really juggle any formulas. So the people who come to this channel with the notion that, oh, math is plugging numbers into formulas, there were no formulas over here. We did not plug any numbers into any formulas, but we still did valid and legitimate mathematics. That's one thing. The other thing I want to bring your attention to is, again, step back and think about the following idea. Knowing absolutely nothing about the sequence, remember that sequence that we mentioned earlier, A, B, C, C, or whatever, knowing nothing about this specific sequence, in other words, knowing nothing about the exact concrete and specific details of how the bananas and pineapples were picked, we still managed to produce an answer to which the notion of absolute certainty can be attached over here with our reasoning about bananas and the parity of bananas on the magic tree with respect to all the harvesting choices made by the person who is doing this is absolutely solid. To that notion, we can attach the idea of absolute certainty. There is no guessing probability or maybe it's over here. Rock solid reasoning. And again, not knowing anything about the specific detail of how pineapples and bananas were picked, we still are able to answer the question of this problem. This is really one of the amazing aspects of mathematics. In any case, now we're done with the problem S2E45 and we will move on to a new challenge next. Our next challenge will be a problem in mathematics. S2M48 is shown over here, and in that problem we're given a 4x4 chessboard that is complete, nothing is cut out, all 16 squares as shown over here are present and available. We're also given 15 plus signs and 1 minus sign. Then what happens is the following. We take the minus sound and choose at random any which one square of the 4x4 chessboard. Onto that randomly chosen square, we drop that minus sign, and once that decision is made, the minus sign is in some square of the 4x4 chessboard. We grab the remaining 15 plus signs and drop them, sprinkle them over the board, over the remaining 15 squares. 1 plus sign per square, so each square is occupied. There is either a plus sign or a minus sign in each square of the 4x4 chessboard. Then the rules of the game are very straightforward and are the following. We're allowed to pick any one row, which one doesn't really matter, any row, or we are allowed to pick any one column. Which one we pick also does not matter, but we explicitly are not allowed to pick any diagonals, and we're not allowed to select multiple objects or mix and match them in any way. In other words, we're not allowed to pick multiple columns. We cannot, for example, pick this column and this column. And we're not allowed to pick multiple rows. It is illegal to pick, for example, this row and this row, or this and this one. It is also illegal to mix rows and columns. We cannot, for example, pick this column, and this row, or for example, this row, or this row in this column. This is not allowed. One column at a time or one row at a time. Once that choice of the object, one column or one row, exclusively one row, is made, within that object, it is allowed to change all the plus signs to the minus sign, and at the same time all the minus signs to the plus sign. Again, for example, let's say we pick this here column. This is it. For one legal move, this is all we can do. And in that column, we roll through the column. All the squares or all the signs must be acted upon, and we go like this: plus, flip it to minus, plus, flip it to minus, plus, flip it to minus, plus, flip it to minus. Or if we pick, for example, this row over here, we roll through all the squares of that row, and this plus becomes a minus, this plus becomes a minus, this minus becomes a plus, this plus becomes a minus, and so on. This is what a legal move is: one row or exclusively one column, and all the squares in the chosen row or column, the signs in all the squares must be flipped to their opposite. So the question now is the following. What do you think? Is it possible in a finite number of legal steps to put the board into a state that is in which the board is filled with all 16 pluses? In other words, is it possible to use legal moves only, and in a finite number of such moves, erase, so to speak, the sole minus sign over here out of existence, take it off the board, so to speak, literally, and fill the board 4x4 chessboard with nothing but 16 pluses, again using the legal moves only and nothing else. What do you think? Again, just to make sure that we all understand what is required of us over here, even if we guess the answer correctly, yes or no. Nobody cares about our correct guess, but everyone cares about your ability to generate a story behind why the answer that you gave is what it is. This is it for this episode. Thank you very much for your time. Thank you for watching. Good luck with this problem. I will see you in the next episode, in which I will share my solution of the mathematical problem S2E45.